Okay, guys, video here. It's on ANCOVA, and after the previous video on covariates, you should have a pretty good understanding of why we include covariates in some studies. Things to think about ANCOVA is just an extension of ANOVA, but we include usually a continuous variable or a quantitative variable that we call covariate, and we expect a covariate to be related to the dependent measure. What we're trying to explain, and the advantages of ANCOVA is it will reduce the error variance, or at least we should. If not, then the covariate had no effect, and we eliminate the confounding results. At the end of the day, for number 2, what I want you to do, it just gives us more experimental control and allows us to tap in more to the treatment and the effect of the treatment. So, guys, there's a study that was done, a data set I'm going to use, and it's by Field in 2010, and it's the effects of Viagra. And what they first did in this is they just ran an ANOVA, and they measured as Y the libido, and I'm really, to be honest with you, I don't know how they measured that, but I do have the data set, and X was the dose of Viagra. As you probably know, I found this this book that's got all kinds of just crazy data sets. So I'm seeking to find the most absurd ones that I can as my illustration. Just consider it me trying to entertain myself. All right, so now that you realize your statistics professor's a wacko, or likes to be entertained by crazy stuff, let's go for it. Okay, now if we were going to run this, clearly we would run just an ANOVA, and the doses of Viagra. I think. I'll have to check on this, but I think it was just they had a placebo, and I think there was a low dose and maybe a high dose. I think is the way it was. We'll see once we get the data set downloaded. So, guys, what we got here is we've got a continuous measure, the libido, over 3 groups. So it's a classic situation to run an ANOVA. Well, Field and his partners, research partners, thought, well, you know what? What if we come in and examine the participant's mate's libido? And I think in the in the article it talks about it takes 2 to tango. So they thought that the mate's libido may be affected, or I'm sorry, the participant's libido, which is our Y, may be affected by the libido of the mate. So they came in and brought this in as a covariate, and I'm going to illustrate this for you. Okay. Now let's just formulate what are we doing here. We have the participants, libido, and I really don't know how they measured that. But I know it was, we'll take a look at that. And we have a factor of dose, and again, dose is placebo, low and high, I'm pretty sure. And then we come in with X2, which we call the covariate of the mate. Okay? Now, what I want to do now is I want to get out of this blackboard and go to R. And let me show you what I've got going on here. First thing, on my desktop, I have libido. I will upload this to Blackboard very soon, and so you'll have that when you watch the video. So I'm going to need that to get that, and of course I've already got R up. So actually, I'm ready to to do some stuff. Now, one thing that that we need to talk about. Let me go back to the blackboard for this. Is just like ANCOVA, we have assumptions, and if you remember, the assumptions for ANCOVA are equal variances, and normality, and obviously, we always want independence. Well, ANCOVA has added assumptions. And the added assumptions of ANCOVA is we want independence of the covariate and the treatment effect. And the second thing is a little more complicated. We need what's called homogeneity of regression slopes. Okay, now what do I mean by that? The first thing, let's talk about this one first. Independence of covariate and treatment. The only thing I mean there is I don't want my my covariate I'm going to write this down. I'm not talented enough to talk and write. I want my covariate, it should not differ over the treatment levels. Now, let's think about in this example right here. Our covariate is the mate's libido. And my treatment levels are the doses of medication. Well, actually Viagra. I don't guess that's really, I guess it is a medication. So what we're saying here is before we ever start to check this assumption, we would want to run an ANCOVA of the covariate over the doses to make sure there's no difference. So this is one place where we actually go in with an intent, and when we hope we run that, we want to run it and make sure that we don't have statistical significance. In other words, we don't want the mate's libido to vary across the placebo, or to be different across the placebo, low or high doses. So again, we'll run ANCOVA to test for this assumption, and we hope that we get not a result that's not statistically significant. If we get a statistically significant result, then we've violated the assumption. The second one that we run into is equal slopes. And if you can imagine this, imagine us looking at x's and y's, and on the x, let's put our covariate, and on the y, let's put the y. And in this case, this is going to be the partner's libido. And we come in and we do this scatter plot, right? And we get something like this. Now, what we want is we want to be able to come over here for the treatment levels. So the placebo, the low, and the high treatments. And let's just say, for the sake of kind of running through this together, that placebo is blue. And let's go, the low is yellow. And let's go, the high is red. Now, let's say that we come in here and we've got these points. And we fit a line to it. Hope you guys can see that. And then we come in here with our blue. And we fit a line to it. And then we come in here with our yellow points. And I'm just making this crap up, so okay. And we come in with our yellow. If we don't violate the equal slopes assumption, then the yellow line, the red line, and the blue line are going to have equal slopes. Now, if we get in a situation, for example, let's say the blue wasn't quite this nice, and the blue looks something like this. Hopefully you can see it's starting to look like a... And we had a blue line, the line of best fit for the blue points look like that, then we have an issue with the equal slopes. In other words, we can go ahead and do it whatever we want to do in R. We can run our analysis, but the results are pretty much meaningless because of the violation of the assumptions. So these are going to be things that you're going to run into from time to time. Let me go back and change my thing back to white here. But again, we want independence, the covariate in the treatment, and we want equal slopes. Okay. Now, there's a really fancy way to test this equal slope assumption, and I'll point that out to you. Okay. Now, we're about ready to make some stuff happen. Now, guys, I'm going to go ahead and warn you. The R commands for ANCOVA are crazy. Okay. They are nuts. Lots of stuff going on here. So, I think in one of the earlier videos I said treat lectures as if, treat videos as if they're lectures. Take notes. You're really going to need to take really good notes on this one. Because what we're going to do when we come in here I think we meet this Friday, we're going to come in and you guys are going to get in groups just like you did last week, and you're going to run some ANCOVAs and ultimately, type up your results and submit them for a grade. So this is going to be an important video for you to take notes, and probably even more importantly, guys, get the R commands down. We're going to get into some crazy stuff when we do the post hoc analysis, which are actually kind of contrast comparisons. Yeah, some of that stuff gets absolutely nuts. I just hope that I can carry it. I hope I can do it. Okay. All right. So let's go to R, and so let me try to get things a little bit more comfortable for me here. Move some things around. What I'm doing today, in case you care, is I'm actually recording this on my laptop instead of my main computer. So I just want to see how that works out. All right, guys, let's get it going here. First thing I'd want to do is I'd want to set my working directory. And since my data is on the desktop, for obvious reasons, I'm going to set it for desktop. Next thing I want to do is I want to go get my data, and I called this libido. And before I get too crazy, I want to attach my data. And guys, everybody likes to look at their data. And now what's going on here? X1. I have no idea why this stuff over here is doing that. Let me get out of here and go take a look at this, because I don't really like that. It's probably not going to affect anything, but oh, I see. It's got just two. Yeah, that's fine. It's just got some information there that shouldn't affect us. Knowing my luck, I'll get halfway through the video and find out it does affect it. So guys, what you can see here is we've got this thing set up correctly. We've got our cases. So participant number 1 has a libido of a 3. Mate is a little more frisky with a libido of 4. And in the treatment effect, they were given a placebo, or the participant was giving a placebo. Come on down. Number 18 is quite interesting. Participant's extremely frisky, yet the mate's not, and the participant was given a high level of treatment. So that should play out to be quite interesting there. Probably not a data set I would use for my undergrad, but we're all adults here, so hopefully it's okay. If it's not, just chalk it up to your professor being nuts. Okay, so guys, let's start out and make it happen. First thing I would want to do is take a look at some descriptives. And while you guys are getting ready to do that, I'm going to go to Blackboard over here and write this stuff down. Okay, I got a call from somebody. Dr. Maxon, she can wait. I'll tell you what, hold on, let me shoot her a text and okay, so guys, let's get some stuff going here. Sorry for the interruptions there. I've kind of got myself. I'll go ahead and tell you, we have some drama in the department. Not drama, but one of our colleagues sent an email yesterday, and she's accepted a position elsewhere. It's Jenny McKinney, and we all wish her well. She did a great job while she was at Shawnee, but she's going to be really, really hard to replace. So, I'll just let you in on why I'm distracted, and I know it's why Krista's calling. Okay, gang, let's do some descriptives, and the very first thing I would want to do is look at a histogram of my measurement on the libido. So, and I'd want to make sure that this distribution looked like it came from a normal distribution, and right off the bat, we got a red flag. So the histogram of the participant's libido is clearly positively skewed. Could that distribution come from a population distribution that's normally distributed? It could, but I don't think it's likely to think that it did. So, violation. So let's just in case, let's say that research shows that the violation of the normality assumption is not a major deal in ANOVA and ANCOVA. But, well, I'm not going to say, I know what's going to happen here, so again, violation number 2. So we've got too many red flags here in terms of just the kind of the ANOVA part. Okay, again, too many red flags. But nevertheless, let's go ahead and run some descriptives. So, guys, I would want to run T apply, and I would want to do this over part and over dose. And the function, let's go the mean. So, for the participant, the placebo is 3.22. The low is 4.88. And the high was 4.85. All right. So again, I'm writing this stuff down on the blackboard, so we'll have it when we go back over. Next thing I'd want to do is I'd want to do the T apply for the mate. And when breaking this across the mate, we get the high libido of 2.00. We get the low of 3.13. And we get 3.44 for the mate of the placebo. That's kind of interesting. All right, we'd also want to get some standard deviations, so I would do the same thing. And guys, I think I can just do SD. Yeah, turns out I can. So for the partner, or I'm sorry, for the participant, we have a 2.12. Standard deviation for high, 1.46. And we have a 1.79 for the placebo. Alrighty, T apply. We want the mate. Dose SD. And we have 1.63 and 1.73. Hopefully you're writing this stuff down just like I am. And 1.63. Okay? Now, just to give you an indication of what I'm doing here, well, I've lost connection, so let me try to get this backing up. All right, so here's what I'm doing. I'm just writing this information down. Now, guys, from what we did before, what would be... Okay, this thing's in a funk. Okay, there we go. Now, what we'd want to do next is we would want to use this information to test equal variances. So if I look at the largest standard deviation, and which is obviously going to create the largest variance. So the largest standard deviation I have here is 2.12. So I want 2.12 squared over the smallest standard deviation. So that's going to be 1.46, so we'll create the variance of that. If the assumptions haven't been violated, then this ratio should be less than 2. And as I've looked into this stuff, now we have Levine's test of equal variances, and there are others too. And I forget the name of the one, but yeah, I know it's two guys. Uh, but this is about as solid a way of checking the equal variance assumption um, as I've found. Now, unfortunately, we get this to be, I think, 2.11, right? Which is greater than 2, so, another red flag. Now, is that, if, for example, if I were contracted by someone to do an analysis, and they decided that I decided the research question that they wanted to take a look at needed an ANCOVA, and let's say that I'm doing this for money. I'm doing this for when it really counts. Would I have problems with what I've found so far? Yes, I would. Would I have enough problems to search for another statistical technique to address the research question? Not yet. And the only reason is I've seen the research on this, and I think I've mentioned there's a guy out of Cincinnati, Stevens, who's really done a lot of stuff on this, who's found that violating the normality assumption and the equal variance assumptions aren't as drastic on the stability of the p-values as once thought. So, I would still go ahead and run the analysis and let it happen. Okay. Now, we have assumptions now for the ANCOVA. So again, remember, ANCOVA assumptions are the same as ANOVA, but ANCOVA has two additional assumptions. Okay, so our first assumption and if you remember back, I want to get my language. Let me think. How did I put that? I think I called it is independence of the covariate over treatment effects. I'm not really sure that's the way I said it, but I think that's close enough. And then we need our second assumption is homogeneity of regression slopes. So let's check the first one. And what I would do here is I would just check an ANOVA. So I would do run an AOV of the covariate, which is the mate over dose. And really can't get much from that. I would want to run a summary actually of that. And when I run this, I look out here and I look at this value right here, the p-value for the ANOVA, and it's greater than 0.05, which means that we would fail to reject the null, which means that we can assume that the means for libido of mate across the levels of dose are not different. So we're not violating the first assumption. Now the second assumption, I'm not going to do because this is going to be a long video here anyway, but what I would need to do for the second assumption I would need to create 3 scatter plots with the linear regression line plotted. And I'd need to do one for, let's see, X equal my mate, Y equal the libido for the participant, and the placebo. The second one I would do would be X is my covariate, Y is my participant libido, and I would want to do it for the low doses. And then I'd want to do one for the high doses. And so I'd have 3 separate scatter plots, and I would just analyze the slopes of the line of best fit and hope that they are the same. Now, I'm going to show you another way. We can do something a little fancier in the end to see if we violate that. We can look at what's called an interaction effect, which we typically don't do. But all right, gang. So this assumption seems to be to not have been violated. So that's cool. Now, what we want to do next is let's run our ANCOVA. So to run let's run an ANCOVA of the participants' libido over dose. Now, I want to do this for a couple of reasons. Typically, you do run the ANCOVA first, just to just to get an indication of the variation of the in the model without the covariate. So guys, the way we would do this is I would run a summary AOV of participant over dose. Okay, what did I do? Oh, my bad. Okay, now something I want you to point out here is I want you to point out the sum of squares. So look at the sum of squares here. So we got 16.84 for the dose. So that's the explained variation. Let me go back here and make sure that I'm... Okay, so in our model, I have no idea why that does that. Let's see what's going on. It'll cover up R. So what we've gotten right now is we've got the sum of squares total. And the model sum of squares is 16.84. And the sum of squares for the error is 94.12. Now, if you go back over to this is what I've done. Now, when we add the covariate, here's what we're going to expect. We're going to expect this. Well, first of all, we're going to expect the 16.84 to remain stable. If it doesn't remain stable, then we have issues. The next thing we're going to want to do is this unexplained variation over here, the error. Some of that is going to be taken by the covariate, so we're actually going to have more explained variation, and there's still going to be some error. But guys, by adding the covariate, we're going to expect this 94.12 to be partitioned into 2 variations, sum of squares, explained, not explained. And the 16.84, we're going to expect it to remain stable. All right, think it's going to happen? I have no idea. So guys, shall we run an ANCOVA or ANCOVA? So let's run the ANCOVA with Y equal the participant's libido. X1, as I'll call it, is the dose. And X2, as I'll call it, equals the covariate. So the way we run this, and I'm going to call this model because we're going to be doing stuff with it. I'm going to run AOV, and I want to run the participant's libido, which don't remember what I called that, PART, as a function of dose plus mate. So this is the way that we run in ANOVA. I'm sorry, this is the way we run in ANCOVA. Now we can come in and look at a summary of our model, and we can see what happens. Now, got some issues here. Dose 12.77, by adding the covariate, the sum of squares went up. That shouldn't happen. If we have a stable model here, the sum of squares for the treatment, or the sum of squares, I'm sorry, for the factor, the main term should stay stable. So we've got more stuff going on. But you will notice that the error in our model, 94.12, has been partitioned into two separate parts. 15 out of that 94 can be explained by mate. There's still 79.05 sum of squares, which is the variation in our model that's that's still not explained. All right. Now, this brings in an interesting situation. Okay, what happens with R? Now, if you don't listen to anything else I say in this video, please listen to this one. What happens in R is this. There's different ways to calculate calculating the sum of squares. And by default, R uses what's called a type 1. Now let me make sure I've got this right. Yeah, it does what's called a type 1 sum of squares calculation. Well, okay. And what I mean by that is what type 1 sum of squares calculation is all about is it matters about the way you put the information in. For example, what if I set up model 1, let's call it, and I run an AOV, part over mate plus dose. And if I do summary of model 1, notice I get something different. Sum of squares for the mate was 15.08 up here, and now it's 6.73. So the default on R for calculating the sum of squares, they use what's called a type 1 sum of squares calculation method, which is a sequential method of calculating the sum of squares. The best way to think about this thing, the way it calculates, is, for example, in this situation right up here where I put dose in first, it calculates the sum of squares, and the calculation of the mate sum of squares is a function of the value we got for dose. Down here, we put the mate in first, so the sum of squares were calculated to be 6.73. When it calculated the sum of squares for the dose, it used the information from the sum square calculation for the mate. Well, I don't know about you, but to me, the way we enter something shouldn't affect the overall model. But it does, and it does, quite drastically in this situation. Now, to control for that, what I'd like to do to create the type 3 sum of squares. Tell you, R is fine, but SAS, which is one of the big boys, and or big girls, however you want to look at it, and SPSS, both by default use type 3 sum of squares. So to be consistent with what we would see calculated with SAS and SPSS, the guys will tell you in your 6500 class you're going to take this fall with me, that's a major part of the class. We get into the mathematics behind the different sum square calculations. So that's something you're going to learn a lot about in 6500. It's something I'm going to have to brush up on because it's some pretty complicated stuff. But right now we're just going to kind of put this on our radar, realize that it exists, and that there is a difference. So guys, it's kind of weird to calculate the type 3 sum of squares. What I'm going to do is use what's called drop 1, and I'm going to use my model. So I'm just going to use this one up here. The model that we did up here, I'm just going to use that one. Turns out it's not going to matter because order won't matter. Then I use a tilde period. And what I want to do now is I want to run a test equal to F. Now, what's going to happen now, it's going to give us some stuff. Mainly, I want you to ignore the R, SS, and AIC. But I want you to pay attention to the F values and pay attention to the P values. But notice what happened here is when we controlled for the order that we enter our information, notice that we get different sum of squares. Guys, this is the one that you need to report. So let's be consistent with the big boys and big girls and report the type 3 sum of squares. Now, just to give you, let's do the same thing. Let's do drop 1. But let's use model 1, which again put dose in first. Put mate in first. So tilde dot and test equals and you'll see that we get consistent sum of squares. That's what we want. Now there's advantages to the other. There's situations where that would be advantageous, but I don't want to get into that dilemma right now. Okay. Now, so what do we know? What can we report from this? Although we've just violated the hell out of the assumptions, we can go up here and see that that there's a significant effect on Viagra on the levels of libido after controlling for the covariate, controlling for the mate's libido. So what we could say here is, so how to report what we see up here. We could say that there is a main effect. No. Let's go there as a significant effect of Viagra on the level of libido when controlling for the covariate and then we would come in and report the cool stuff. So we have F, which would be 2,26. So what we're doing here, guys, we're looking at the dose, which has a degrees of freedom 2. And guys, our error term up here has a degrees of freedom 26. So we want this equal to the value of dose, which F is going to be 4.14. And our p-value is less than 0.05. Now the p-values are reported as either less than 0.05, less than 0.01, less than 0.001, or it's reported if the p-value is greater than 0.05, we report it as is. So that's how that I would want you to report this. Now, the next thing we want to do is we want to get into a post hoc. And where exactly do these differences lie? Maybe, for example, I don't know, the higher dose is affecting our model. Maybe the lower dose, maybe a placebo, maybe something strange happened with the placebo, which is kind of crazy because that's actually the way I think Viagra was actually found. I think it was actually originally, I forget, it was to treat something, and then they noticed this this crazy unintended outcome, and decided to capitalize on it. So guys, what I want to do now is I want to introduce you to the first time to what we call contrast. And the pairwise comparison that we think about with ANCOVA, which would be the Tukey, is not appropriate for ANCOVA. What we're going to do here is we're going to do what's called contrast comparisons. And contrast allows you to go in and weight contrast to weight the means. And there's even a more clever, unfortunately much more sophisticated way to do all pairwise comparisons. Weight everything the same and compare everything to everything else. Now, to run this, we've got to do some stuff. And the first thing, we've got to install a package. The package that we have doesn't handle pairwise comparisons for ANCOVA. So the first thing I'll do is I'll install the package, and it's going to prompt me to choose a CRAN. And guys, I don't even know why I do this, but I always just choose USA California 1. Now, when you do that, your R is going to go through some stuff. And it's going to be jumping around like it's lost its mind and do some stuff. And pretty soon you're going to see where you've got a prompt where you can enter R commands. So you can see mine's still working. Yours probably is too. And it takes actually quite a bit to get this downloaded. All right, so everything's been downloaded. Now the next thing we got to do is we've got to come into library of multcomp. And it's loading some required packages. Now guys, if you don't do that, you're not going to be able to carry out the pairwise comparisons. And again, unfortunately, there's not a nice, neat Tukey HSD that does this for ANCOVA. Now, guys, this is something you're probably going to need to pause me. The commands here are absolutely crazy. But the first thing I'm going to do is I'm going to do model tall. And I'm going to set up my interactions. So width is a command that allows me to set up interactions. So this model $tall is just a way of communicating with R that I want to set up interactions. And actually the tall there is not just something random. Doesn't mean we got tall people that are got big libidos or what, you know, has nothing to do with the data set. It's a command with R. So we go with data, and then I want to set up interactions. And I want to do dose. And I want to go sep equal X. So nothing happened, and that's good. The next thing I want to do is I want to set up my general linear model. So I have M1. I'm going to set up a linear model of my Y, which is participant's libido, over my covariate, which was mate. n plus tall, and our data equals data. Okay, what's going on? Tall not found. Called it data, called it model. Okay. Okay, there we go. So that's M1. God, I don't know what I was thinking about. We set this interaction as model tall, and I lost my mind and did that. Now the next thing I want to do, let's get this where you can see it, and I want to set up L1. And we use what's called a GLHD command. This is a general linear, what is it? GLHD is something general linear something distribution. But it's a command that allows us to come in and perform comparisons. Doug, you're losing your mind here. Okay, what's going on here? Well, this is no fun. And, oh, I know what's wrong. GLHD, this should be M1. This should be len fact equals MCP. Tall equals 2. Yeah, I think this will work. Well, guys, this is fun. GLHD M1 len fact equals MCP model dollar tall equals 2 key. Well, guys, I don't know. Let me work on this one. Okay, I don't know. I just crashed and burned. I actually ran this before and it worked perfectly. So I'm not really sure what happened here. It's not finding GLHD is what... Oh, no. That's not right. Okay, gang. I think I've... General linear hypothesis test. All right, I'm going to try one more thing. GLHT of M1 is what we want. Land fact equals MCP. Model $tall equals Tukey. Okay. Well, this is no fun at all. Okay, I've got the right command. Okay, I'll tell you what. I'll work this out. There's one more thing that's really important that I want to show you. I've got something off a little bit. I don't know what it is. You know how this stuff is. There's one thing I want to show you. How kind of a fancier way to examine the second assumption. Remember, the second assumption was the homogeneity of regression slopes. A fancier way is to construct construct an ANCOVA with the interaction effect. And if the interaction effect is statistically significant, then we don't have equal slopes. We don't have homogeneity of regression slopes. So something I could do here, and I'm just going to set this up as like model 99. Is I could run an ANCOVA of partners libido over mate, but this time let's do the interaction with dose. Now, guys, typically we don't do this in ANCOVA because think about it. Mate is quantitative, and we do interactions of two categorical variables. But nevertheless, it's kind of cool that we can do this because it gives us a fancy way of, oh wow, I didn't, okay, so it gives us a fancy way of examining the regression slopes. So mate and dose, if we look at the interaction here, we have 0.0277. Now, granted, this thing is is calculating type 1 sum of squares. So remember, if we want to do a type 3, we're going to do drop 1, and I'll do model 99 tilde period test equals F. But it's not going to give us anything different on the interaction, I don't think. Let me make sure. Actually, it does a little bit. 20.43. No, it doesn't. How can I say it's not supposed to? Okay. But anyway, you can see our F, and what's most important here is our p-value. So, guys, we've violated another assumption. So, at the end of the day, if I was doing this for money, we have violated from the ANCOVA perspective, we violated the normality assumption. We violated, just barely, but the equal variance assumption. And we have violated one of the biggies. In ANCOVA, we've violated the homogeneity of regression slopes. So, guys, I would probably step back, think about doing some transformations on the data. We haven't covered that yet. Also would consider maybe running a non-parametric design, which we'll cover here in a couple of weeks. So, guys, this is the violations here are extremely problematic. Now, I don't know how far I am into this video, but what I want to do, I'm going to put this video up and then I'll put another one up, is I want to examine these slopes. So I'm going to end this video right now, and then there's going to be another video up that where we examine the slopes and just try to get a visual on why these things are being violated. Okay, so guys, have a good one. This is an important video, man. It really is. I know. I'm afraid some of you are not watching the videos like you're supposed to. You're only going to have 3 videos this week, and no assignment other than your write-up from last Friday's class. So, guys, you got to watch these things. When you come in here on come to class on Friday, I'm going to assume you've watched this and going to hold you responsible for it, because this is what we're going to be doing. So, guys, have a good one. There's going to be one more video that'll be brought up.